Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today I want to talk at kind of a high level about some ideas in algorithm and data structure design and how they relate, how theory and practice relates, and how theoreticians, or how I think theoreticians should approach these areas. And I'll illustrate some of these concepts with two problems that I've worked on over many years, but there are still things to be learned about these problems. So I'll talk about some new work, but start out with the classical work. So let me begin with some general observations. You know, the AVL tree, which was the first balanced search tree, was invented by Adelson, Velsky, and Landis, two Russians, in 1961. And actually, Adelson Velsky just died last month. And since that time, and even since earlier, theoreticians, computer scientists, mathematicians have developed many beautiful asymptotically efficient algorithms. But many of these algorithms are very complicated and have not yet been used in practice. And many of the theoretically efficient algorithms, when used, don't work so well in practice because they have high constant factors, or people are ignoring logarithmic terms, or they're just too hard to implement. And sometimes the theory says the algorithm should be good, but simpler methods work faster for somewhat mysterious reasons. So we'd like to understand this phenomenon. So first of all, of course, implementers, programmer time is much more valuable than computer time. So implementers, when faced with a task, will choose the simplest possible way to get it done that meets the needs of the problem. So it is only in situations where you have a basic task that you want to solve repeatedly, or you have large instances, many large instances, that you need to think about sophisticated algorithms. So Einstein said something like, make everything as simple as possible, but not simpler. This is our goal, to use the best possible algorithms in the situations as required. All right. Now here's another interesting thing, which is that data instances are not necessarily worst case. Some of us design algorithms to meet worst case needs, but the problem instances that come up are not worst case. They come from some kind of distribution, which we cannot necessarily model probabilistically either. So average case analysis does not necessarily apply, although I'll give you an instance where it does apply. Practical instances sometimes have some structure that we can exploit through the algorithm. So the goal then is to, instead of designing a general purpose, worst case efficient algorithm, to design an algorithm that's simple and exploits the structure that actually arises in practice. All right, now, so my goal as an algorithm designer is to try to develop and analyze simple methods, apply theory to analyze methods that actually get used in practice, and to improve those methods. Take heuristic methods and turn them into verifiably efficient methods. Take complicated methods, make them simple. Find the structure in the data and exploit that structure in the algorithms. All right. So Paul Erdős, who was a famous mathematician who collaborated probably with more people than anybody else, had this idea of proofs from the book. This is the book upstairs. It's a beautiful idea. Design a proof as simple as possible. It really captures what is going on. And in the same way, I think it's important to try to design reference algorithms, or algorithms from the book, that are as simple as possible. Maybe they have some mysterious properties that we can capture in the analysis, but the algorithm should be really clean, easy to code, efficient in practice, and with provable resource guarantees, at least on important input classes. All right, this is all a little bit highfalutin, so let me talk about two one data structure and one algorithm that are tied together in interesting ways and on which there has been work over several decades. The first data structure I'm going to discuss is a data structure for maintaining disjoint sets, or equivalently equivalence relations, or maintaining the connected components of a graph when we're adding edges. And the data structure to solve this problem is a compressed tree. So in this problem, we want to maintain a partition of a fixed set of elements. We can think of adding additional elements, but let's, for simplicity, just imagine that we have a fixed set of elements. We're going to be combining disjoint sets, and we want to identify each set somehow. And we'll identify each set by an element in it, which I'll call the root. So we can store information about the set with the root. Data structures for this problem, as far as I know, first arose in Fortran compilers. In the old days, computers had very little memory, and it was important to reuse the memory by sharing variables and overlapping arrays and so on, and that naturally leads to this equivalence problem. And also, this data structure that I'm about to describe comes up in Kruskal's minimum spanning tree algorithm and other graph algorithms, and in percolation, where we're trying to find paths between sites in some kind of a network where edges are getting added. Okay, so to be a little bit more precise, we want to maintain sets under three operations. We can create a new set containing a single element that is in no other set. We want to be able to do a lookup operation, which I'll call a find, which returns the root of the set containing the element x. So that's essentially the name of the set. And the important update operation is unite, which, given two elements, if they're in different sets, puts the two sets together into a single set. And if they're in the same set, doesn't put them together. In the case, and returns a Boolean value that gives you the outcome. So if x and y are in the same set, this is set up to return false. Otherwise, if they're in different sets, we combine the two sets containing x and y, pick a new root from among the items in the unified set to name this set, and then we return true. So if you prefer true to be x and y are in the same set and false they're in different sets, feel free to change. This is natural in Kruskal's algorithm, where this is the key operation. All right. Now there's a very simple implementation of this abstract data type, which is to just represent each set by a rooted tree whose nodes are the elements in the set, with every node having a pointer to its parent in the tree, and we'll make the root point to itself. So we can walk from any element to the root of the tree containing it, and that root is the set root. The tree root is the set root. So it's simple to do a find operation. We just walk up the path in the tree. The shape of these trees is completely arbitrary. All we have to maintain is that each set has its own tree. And I'll denote by n the number of elements and by m the number of finds plus unites, the total number of operations. And I'll assume that the parameters are non-trivial. So we got at least two elements, and we're doing, say, at least one find on each element. This is just for simplicity in stating time bounds. All right, so to make a set, we just make x point to itself, and x is a singleton set, its own root. If we want to do a find operation, we just follow parent pointers from the node x to the root. And if we want to do a unite, we do a find on x and on y, which gives us the two roots of the trees containing x and y. If they're equal, we don't change the data structure. If they're different, we'll do what I call a link and return true. And a link just makes one of the roots point to the other. These are the roots v and w. And we have some flexibility here. We can make V point to W or W point to V, and we'll exploit this choice in a minute. All right. Now, the trouble with this naive implementation is that we can easily create a long path, and then we can do repeated long finds. So this costs us order n per find, which is a total of order mn for m operations, which is not too happy. Our goal is to get much closer to constant time per operation rather than linear time per operation. Okay. And we're not concerned about the individual time of operations. We're willing to allow some operations to be expensive if that makes other operations cheaper. So I want to just mention this notion of amortization, which captures this idea. We're interested in the total time of all the operations, which we can then divide by the number of operations to get what I'll call the amortized time per operation. And the links are constant time, the make sets are constant time, everything except the finds are constant time. In order to improve this data structure, we need to reduce the lengths of paths in these trees. And there are two ways of doing this, both exploiting the design flexibility we have here that the shape of each tree is arbitrary. This is the most primitive use of a tree data structure. You can use trees to implement priority queues. That's the data structure that was discussed in the previous talk. Or you can use them as search trees. Here, all we need is a parent pointer per node. The shape of the tree is arbitrary. Let's see what we can do with this. So the first thing we're going to do is exploit the freedom in the links to basically make the root of a small set point to the root of a large set. Now that's the idea of linking by size, which is the original version of this improvement. I'm going to talk about a slightly different, more efficient version, which is called linking by rank, where we measure the size of a tree by the maximum path length, the height. And then we'll talk about modifying the trees during the finds to squash the paths. Again, exploiting this fact that the shape of the tree is arbitrary. Okay, so linking by rank, we add to each node a non-negative integer value, which we'll call the rank, which is a 0 for a single node. And we always make the root of smaller rank point to the root of larger rank when we're doing a link. The only ambiguous case is if we're trying to link two roots of the same rank, and then we'll increase the root of the rank of one root by 1, and now link the smaller to the larger. So here's an implementation of the link operation with this kind of rule. Now, this very simple linking rule guarantees that the maximum path length, the height of the tree, is reduced from linear to logarithmic. Because in order to build a path of length 1 greater, you have to put two trees of roughly the same size together. That all by itself reduces the time per find from linear to logarithmic. This is a worst case guarantee now. Now the other thing we can do is change the tree when we do finds using some kind of compression strategy. This strategy was invented by Alan Tritter, who was at IBM many years ago in an implementation of Fortran equivalents and common statements. So the idea here is that when we walk up a path in the tree, we've got the answer, we've got the root, not just for the original node, but for every node along the path. So let's make every node along the path point directly to the root. That will reduce the time for later finds from whatever the path length was to constant, in fact, until we start adding more roots on top. So here's an implementation, a recursive implementation of find with path compression. This implementation walks up the path to find the root, then unrolls the recursion walking back down the path to set all the pointers. You can also use 2 passes over the find path and implement this iteratively if you want to. And just to make this clear, here's an example. This is a tree representing 1, 2, 5, 3, 4, 8, 7, 10. 10 is the root. It points to itself. If I want to do a find on 1, I follow the parent pointers. 10 is the answer. And if I want to do compression, I then make all of these nodes point directly to 10. Like so. So this flattens the tree and really improves things later on. I pay a factor of 2, more or less, in the find operation locally. But I compress the tree and save time later on. So this is a situation where amortization is very important. We're going to get cheap finds later on for by paying extra on this particular find, but only a constant factor. Okay, now one can criticize the fact that we're doing 2 paths over the find path in order to do compression. We can also do compression with only 1 pass, and there are various ways to do it. Here's perhaps the simplest, path splitting. When we walk up the find path, we make each node point to its grandparent, so we only have to look ahead 1 node. And here's a purely iterative implementation of find with splitting, and here's the illustration on the same tree we had before. So now if I do a find on 1, I'm going to make every node point to its grandparent along the find path. So 1 points to 5, 2 points to 8, 5 points to 10. 8 doesn't change, 10 doesn't change. So this also compresses the tree, but not by so much. It splits the original find path into 2 paths, each of about half the length. All right. Now, how do these methods perform? In particular, how much improvement do we get out of path compression? It turns out to be perhaps surprisingly non-trivial to analyze what's going on, because you have to analyze a long sequence of operations. If you use naive linking, that is without linking by rank, but one of these path compression strategies, then you reduce the time per find to, again, logarithmic, and it's actually logarithmic with a base here that depends upon the ratio of operations to elements. So as the density of operations increases, this goes down, actually. So this gives, all by itself, path compression gives at least as much benefit as linking by rank. Now the question is, what happens if you put the 2 ideas together? This is the algorithm that Tritter used in his Fortran compiler, and Knuth, back in the late 60s, early 70s, posed the analysis of this data structure as an open problem. And it's surprisingly non-trivial to analyze, and it's got a non-trivial answer. So shortly after Knuth posed the problem, there were a couple of famous theoretical computer scientists, who I won't name, who gave a constant amortized time bound for this data structure, which turns out to be invalid. Mike Fisher in 1972 got a log-log upper bound. Hopcroft and Ullman improved it to log star, and then I was able to show that the real answer is inverse Ackermann function. And to illustrate the fact that this is fairly non-trivial, this analysis, there was at least one later false proof of a lower bound of log n, which couldn't be true if this is the right answer. I'm not going to go through this analysis, but I just want to define what the Ackermann function is here, because it's kind of interesting. My proof uses a sort of a bottom-up analysis. There's a completely different top-down analysis that was proposed relatively recently. All right, here is Ackermann's function. This was originally proposed back when logicians and computer scientists, pre-computer scientists, Turing, were trying to define computation. And the logicians' approach was general recursive functions with multiple variables. And Ackermann designed his function to show that single variable recursion is not sufficient to generate all general recursive functions. It's a 2-variable recursive function that grows faster than any single variable recursive function. And here's the definition. The key part of it is these are the boundary conditions, and this is the important thing. AKJ, think of K as defining the kth function in the family. So we get the kth function in the family by taking the k minus 1 function in the family and applying it to itself j times, essentially. That's what this is saying. And the 0th function is just the successor function. This other piece of the initial conditions gives that the first function is just the plus 2 function. This doesn't look so interesting. But the second function here is not plus 3. It's really twice. It's multiplying by 2. And then the third function is exponentiation. And the fourth function is essentially iterated exponentiation, tower of 2s. And this thing grows really rapidly. If you plug in small values here, you get giant numbers. The inverse function, the inverse Ackermann function that I denote by alpha here is essentially, well, the functional inverse of this function. The details don't matter too much because this thing grows so fast that any reasonable inverse function, all possible inverse functions are related to each other by an additive constant, in fact. All right, now this very simple algorithm has this incredibly complicated running time. This is both a lower bound and an upper bound. The proof on both sides is complicated. Good. So here's the story. Compressed trees with path compression or splitting and union by rank take just over constant time per operation in theory. Ackermann function you can never detect experimentally. It grows too slowly. In fact, Seidel and Scherer's analysis, they did a very careful, tight analysis, and their bound on the number of pointer changes is something like the number of finds plus twice the number of elements for any problem size that could be solved smaller than the number of electrons in the universe. So this is a constant for all practical purposes, but theoretically non-constant. And there's this esoteric function that was defined in mathematical logic that comes into play in the analysis of this algorithm. Compression and splitting take something like log time, and this bound is tight. If you ignore the base of the logarithm, these are the theoretical results. So we would say that if we want to take the good algorithm in practice, we should probably take this one, and you can probably detect the difference between constant and logarithmic, even though you're not going to detect the difference between constant and inverse Ackermann function. All right. Now let's turn to a graph problem that starts out completely different, but turns out to be related to this set union problem. This problem also comes up in compilers. It's the problem of computing dominators in a flow graph. So a flow graph is just a directed graph with a start vertex, such that every vertex is reachable from the start vertex. So imagine a computer program with a start point and a flow chart, if you will, or text of the computer code. Blocks of code correspond to vertices, and transitions from block to block correspond to edges. We'll say a vertex V dominates another vertex W if V is on every path from the start to W. This notion is important because if we want to do global code optimization and we have some computation going on inside an inner loop that's repeated over and over, we can pull it out of the loop, but we have to move it to a point where we're guaranteed that we will pass through that point in the code no matter what path we take to get into the loop. So we can move code from some place to some other place that dominates it. So global code optimizers use this notion and construct the dominator tree. The dominators, this is a relationship that has a particularly nice structure. It defines a tree. That is, there is a tree, which I'll denote by D, such that V dominates W if and only if V is an ancestor of W in this tree. So the tree is rooted at the start vertex. And we want to compute this tree. So here's a flow graph. 1 is the start vertex. If I want to get to 9, for example, I have to go through 2. So 2 dominates 9, and so on. And for this particular flow graph. This is the Dominator tree. So 2 dominates, it dominates 7, 8, and 9, but it also dominates 5 and 6. And 6 is dominated by both 5, 2, and 1. So to get to 6, I have to go to 5. To get to 5, I have to go to 2. To get to 2, I have to go to 1. And that's the deepest path in this tree, and this is what I want to construct. Now there's a naive algorithm, an obvious one for constructing this tree, which is just to remove each vertex in turn. First, applications. I mentioned global code optimization. This is a key algorithmic component in every global code optimizer. But there are other less obvious, interesting applications, including in circuit testing and in theoretical biology, analyzing food webs where you're trying to figure out if there are certain species whose removal is going to starve a whole bunch of other species. So the dominance relationship has to do with dependence on each other as food. And actually, whereas program graphs tend to be reasonably well structured, nature is complicated, and the graphs that arise here have no useful structure in computing Dominator trees. Okay. Now the obvious algorithm is just delete one vertex at a time. All the vertices that become unreachable once you remove a vertex are dominated by the vertex that you removed. So you delete each vertex in turn, do a graph search which takes linear time. The total time for this algorithm is vertices times edges, which is certainly polynomial, which is good, but it's not so good in practice because, among other things, the worst case time bound is the same as the best case time bound. This algorithm doesn't exploit any particular structure. If you remove each vertex in turn, the only thing it might exploit is that you can cut the search off early if there's a lot of dominance in the graph. Some of your searches aren't going to explore the whole thing. But essentially, this algorithm, the best case is the worst case. Now, I did my PhD at Stanford exploiting depth-first search to get a fast algorithm for planarity testing. And when one has a good technique, one tries to hammer away at problems. And this is an obvious problem. It's a connectivity problem in directed graphs where depth-first search should help to solve it. But first, back to our example. So here, if you delete 2, 5, 6, 7, 8, and 9 become unreachable, so they're dominated by 2. If you delete 5, 6 becomes unreachable, and it's dominated by 5. And if you delete all the other vertices, it doesn't create any non-reachable vertices. So all the other removals turn out to be useless, but you can't tell that ahead of time. All right. So Tom Lengauer was a student of mine at Stanford. We developed a 3-pass, I'll call it a 3-pass refinement algorithm, or the LT algorithm for computing dominators, based upon depth-first search and based upon a data structure which generalizes this compressed tree data structure that I started talking about previously. So it's 3-pass refinement. It computes an approximation to the dominators called semi-dominators. And from semi-dominators, it computes a better approximation called relative dominators. And from relative dominators, it computes immediate dominators, which are the parent information in the tree structure. And I don't want to go into the details except to note that steps 0 and 3 are very easy, and steps 1 and 2 are the core of the algorithm. And the real effect of this idea is to reduce a graph problem via depth-first search to a data structure problem much like the disjoint set union problem, except that there are now numbers involved, and the specific abstract data structure that we need solves this problem. I'll call it the path minima in trees problem. So now we have trees whose structure is forced upon us by this Dominator algorithm, but they're all node disjoint, and every vertex has an integer value. And rather than walking up paths to the root and returning the root, we want to be able to walk up paths and return the minimum value along the path. So we now have link operations which allow us to hook two roots together. We can create new vertices with predefined values. And in place of the find operation, we have a find min operation, which finds a node of minimum value on the path from x to the root of its tree. And using an implementation of this data structure, we can then plug it into the Dominator algorithm and get a fast algorithm. Now it's fairly straightforward to use path compression here. So we got sort of half the benefits of the disjoint set union algorithm. But because of the fact that we're dealing with numbers on these paths and the link has to go in a certain direction, that is, one of these is specified as the root and the other one is specified as the new child, we don't have the flexibility to do the linking the way we would like to do it to make the trees relatively balanced. So it seems like we can't get the benefits of both simultaneously and get down to inverse Ackermann function. But we did manage to, in fact, do it. So we came up with two versions of this algorithm, one of which uses path compression in a straightforward way and has a running time which is O tilde m. This is linear in m if you ignore log factors. And we also succeeded in getting a almost linear for all practical purposes algorithm. Tom actually implemented both versions of this algorithm, and we were, of course, prejudiced because we liked the complicated algorithm. But in his experiments, the complicated algorithm proved to be slightly faster than the simple algorithm on the examples that we ran, which weren't very big, but not by very much, 10 to 20%. All right. And in fact, because he implemented this algorithm and put the code or pseudocode into the paper, this is the algorithm that is used in a lot of optimizing compilers in practice. Okay. But this algorithm, it's got a lot of moving parts, and even though the code was there, it's hard to think about. So programmers raised various questions about it. An obvious one is, can you come up with a simpler algorithm but similarly fast, linear or m log n or something like that? And a related question about correctness is, how do you know that you've got this thing implemented correctly? Is there some way to verify that the tree you get out at the end is the Dominator tree, other than by doing this naive approach of removing each vertex in turn, which is very expensive? That is, can you make the algorithm self-certifying? Can you somehow easily verify a Dominator tree? We know from the theory of P and NP that verification, at least of certain kinds of problems, is much easier than generating the solution in the first place. Now here we've got a very fast algorithm to generate the solution, but it's complicated. Is there a simple verification test for Dominator trees? I'll return to this question later. Okay, lots of interesting theory. In response to this this question about a significantly simpler algorithm, Cooper, Harvey, and Kennedy in 2003 took a bit vector algorithm and modified it in a nice way to give a new simple algorithm, the tree update algorithm, I'll call it. You maintain an approximation to the Dominator tree, a conservative approximation, and then you repeatedly improve it. And the idea is that if there is an arc in the graph from V to W such that V is not a descendant of the parent of W, then you can replace the parent of W by the nearest common ancestor of V and W in the tree. So if we have let's think about this for a minute. If we have, well, I'll show an example in a minute, but let me just say what this algorithm does. All we need is a very simple representation of the Dominator tree, just parent pointers, as in our original data structure. We can find nearest common ancestors by following parent pointers simultaneously from the two ends of each arc. It's a simple iterative process, but it runs very slow in theory. In fact, it runs even slower than this naive vertex removal algorithm. If you implement it carefully, whoops, you get a worst case bound of n squared m. But this algorithm, the best case is not the worst case. This thing performs pretty well in practice. And these folks claim that it ran very fast in practice, perhaps faster than the LT algorithm that I described. Now here I've got an example. So if we start out with what's a good approximation? Well, let's do a breadth first search of this graph and use this to build our initial tree. So here's a breadth first search tree of this graph, which gives us a superset of the Dominator information. So, and now we notice this edge from 5 to 8. This tells us that we can get to 8 avoiding 9, because there's this path here. So to encode that in the tree, we replace the parent of 8 by 2. And this edge 6, 7 tells us that we can get to 7 by avoiding 8 and 9. So we replace the parent of 7 by 2. And this edge from 7 to 4 tells us we can get to 4 avoiding 3. So we replace the parent of 4 by 1, which is the nearest common ancestor of 4 and 7. So by 3 update steps, judiciously chosen, you can in fact get the correct Dominator tree. But of course, you don't know a priori what order to look at the arcs, and you have to process all the arcs at least once. And the question is, how many times do you have to go through the arcs, and is there some good order to do the processing? All right. So another couple of my students and I did some extensive experiments motivated by this simple algorithm. We experimented with the simple tree improvement algorithm and versions of the LT algorithm, and some hybrid algorithms that used some ideas from the LT algorithm but simplified it a little bit with no time-bound guarantees. And we discovered that the algorithm that's really the right one to use in practice is the simple version of the Lengauer Tarjan algorithm. In these later experiments, it ran much faster, not much faster, 20-30% faster than the sophisticated version. On small to medium-sized examples, the tree algorithm does pretty well, but even on small examples, it ran slower than this algorithm. And on large examples, it can be prohibitively slow, in fact. So this algorithm scales extremely well, and it definitely is the algorithm of choice. Our conclusion was basically that the Cooper et al. Team didn't do the best possible job of implementing this old algorithm, which is experimental algorithms is a very important field, and it's a giant can of worms because you have to be very careful. You can change the results of the experiments by the details of how you implement algorithms. Anyway, now here's another set of experiments more recently done by Patwari, Blair, and Mann, getting back to disjoint set union. They implemented Kruskal's minimum spanning tree algorithm. You have to sort the edges in increasing order by weight, so you need some sorting step or a priority queue or something like that. But the main part of the algorithm is the disjoint set union data structure. So you sort the edges by weight, or you have a way to get the edges out in increasing order by weight, say with a priority queue. The general step is you start out with no trees, add the cheapest edge. If it connects 2 vertices not yet connected, you add it to your growing minimum spanning tree. If it connects 2 vertices already connected in the same connected component, you toss it out. So that's exactly the unite operation the way I have defined it in the disjoint set union problem. And they discovered that in their experiments, naive linking with this one-pass version of compression with splitting beats linking by rank with either compression method. Okay, so now we've seen 2 sets of experiments where simple algorithms with pretty good running times or beating sophisticated algorithms in practice. And the question is this a random phenomenon, or can we, as theoreticians, say something about this? Why doesn't linking by rank, or its equivalent in the LT algorithm, help in practice? Okay. So here we come to this idea of data sets having structure. These experiments that Patwari, Blair, and Mann were doing have an interesting characteristic. Essentially, the naming of the vertices is completely independent. They were experimenting on random graphs and graphs drawn from the real world, and essentially permuting the names of the vertices doesn't make any difference. That is to say, take any graph instance with vertices 1 through n, permute the names 1 through n. That graph that you got with the renamed vertices is equally likely to the original graph. So what does this do? Does this tell us something about these algorithms? Can we analyze these algorithms under this kind of random graph model? This is the problem that we took a look at, trying to explain these experiments using now some theory of random algorithms. All right, so what does this renaming of vertices correspond to? It corresponds to randomized linking. We've got an instance of this disjoint set union problem. We'll identify the vertices by naming them 1 through n with all permutations equally likely. When we do a link operation, we put two roots together. We make the smaller root point to the larger root. We call that randomized linking. Now, my claim is that, in effect, this is the linking rule that was used in the set union experiments. It was not randomized linking. It was randomized linking. It was not naive linking. It was not the worst case of linking. It was this randomized linking strategy just because of the data sets that these experiments were done with. And I think something similar happened in the experiments with the Dominators algorithm, but it's more obscure. So the rigorous claims that I'm going to make apply to set union, and I'll wave my hands about the Dominator algorithm. Okay, so here's an algorithm. This is the algorithm that was getting experimented with. Can we say something about it in theory? Does this behave more like worst case linking or more like best case linking, linking by rank? So we set out to try to analyze this. Now, it's important to note that there are other randomized linking strategies, and an obvious one is 50-50 linking. Flip a coin, and if it comes up heads, make x point to y, and otherwise make y point to x. This one, it's easy to, whoops. It's not equivalent, and it's easy to construct examples where 50-50 linking performs poorly, although we don't have theory to give a tight bound on this one at the moment. We've got experiments to show that this is bad, no theory. On the other hand, this randomized linking strategy, we've got theory to explain that it's good. In fact, now in expectation, because it's a randomized algorithm, it's got amortized inverse Ackermann function time per find. So it's got the same bound as the sophisticated algorithms. You're getting the effect of linking by rank for free out of what the data is, out of the data sets. This is what is happening. And I won't go into details about how this, the analysis works, but I got a few minutes left, so I'll just mention the non-trivial extra pieces we need to do the analysis. With randomized linking, the original inverse Ackermann function analysis uses ranks very heavily and properties of ranks, and the fact that the number of nodes of a given rank is exponentially small in the rank. That's the key point. So all the nodes can have rank 0, but only half the nodes can have rank 1. Only a quarter of the nodes can have rank 2, and so on. And low-rank nodes point to high-rank nodes. And then you get this bootstrapping phenomenon that goes on with the path compression, which somehow produces inverse Ackermann function. So with randomized linking, there aren't any ranks. So we have to introduce ranks into the analysis if we want to mimic that kind of analysis. So we define ranks on the basis of the numbering. We give so we've got the vertices numbered from 1 to n randomly. We give vertices numbered 1 through n over 2 rank 0. Vertices numbered n over 2 plus 1 to 3n over 4 rank 1. And the next eighth, let's see, half, quarter, eighth, the next eighth get rank 2, and so on and so forth. So we get the right distribution of ranks. And we got small nodes pointing to large nodes. Now everything works except for one problem. We can now have parents of the same rank. We can have a node of rank k pointing to another node of rank k. And this breaks the analysis, except that it doesn't happen very much. There's a negative binomial distribution. So if you have rank k, the probability that your parent also has rank k is at most a half. And the probability that that node's rank is also k is at most a half. So the number of consecutive vertices you can have of the same rank in expectation is at most 2. So you don't have these long strings of same rank nodes. In order to do that, you have to do some additional technical analysis that involves converting an arbitrary sequence of links into a special sequence where you just add a node at a time and show some kind of equivalence to the general case. So those are the ideas that we used in the analysis. And once you can handle the same rank case and prove that it doesn't happen too often, you can then call upon the old analysis to get the inverse Ackermann function bound. All right. We also went back and re-looked at the Dominators problem to ask whether it's possible to get rid of this path finding on trees and just use the vanilla disjoint set union data structure itself. And it turns out that there is a way to do it. And it gives equivalently fast algorithms. We've done some theoretical work and some recent experimental work that's just coming out this year. And we also found a way to produce self-certification of a Dominator algorithm. That is, if you add a little bit of extra computation, you can compute a little bit more information so that if I hand you the tree plus the extra information, it's very straightforward to verify that you have the correct tree. So if you're suspicious of your algorithm, you can check the output with a simple algorithm. I think this is important. And this problem all by itself turned out to be rather complicated, although the solution that we came up with in the end is fairly straightforward. Okay, so what are my conclusions? My conclusions are that there's a rich interaction between theory and practice. Don't get stuck. Keep going around the cycle. And look at the structure of data sets as well as the structure of algorithms. Worst case for all possible instances is maybe too coarse a measure of what is useful in practice. And another important thing here is I've talked about a couple of problems that I and other people have worked on now for a number of decades. Classic problems, important problems, still have rich secrets to yield. And I haven't even talked about, for example, concurrency and some of these ideas that were in the preceding talk, which also have a serious role to play here. So let me thank you very much, and I'll be happy to answer questions if you have some.
Being parsed in something like via BFS order or something that you assumed some sort of random labeling, so kind of a random partition of the random stream of nodes. Some of those. Do you get anything for BFS?
Well, that's something we want to look at. I haven't had a chance to do it yet, but these results on disjoint set union strongly suggest that with some of these graph algorithms, you could exploit the randomization that's built into the data structure. I think it's something interesting to take a look at.
Just a second quick question. What happens if I want to remove edges from the graph?
With disjoint set union, it's a beautiful problem. It's more complicated. There are polylog time algorithms. I can send you some references if you want them. Yes.
So when you were hunting for the difference between what you saw in practice and what you expected from theory, did you investigate the possibility that the cost model that you used in theory wasn't really accurate with respect to what was used in practice? So
that's a very important question. Obviously, there are many ways to answer this question. There's been a lot of work on I/O model and memory hierarchies and so on, which I think is very important. It's complicated enough to look at simple models. Now, I don't have a good answer for you. I think you got to try to look at the most realistic model that you can, but don't overcomplicate things. Because, for example, memory hierarchies change over time. We're getting larger and larger flat memories, so some of this early work comes back into play again, I think. So I've found enough richness in the simplest possible memory models, but it is important to look at memory hierarchies.
Yes, yes.
Apart from the randomization of the node labels that you can induce, did you consider the fact that the trees the graphs you were considering were themselves coming from some particular distribution? Or?
No. Simple answer is no. The answer is we wanted to make minimalist assumptions, and since you can prove good behavior just with this simple assumption, which seems to be true in the data sets, I'm happy. I think probabilistic models are very dangerous. If you have control over the model, that is, you're running a randomized algorithm, or it's sort of obvious in the data, like certain sorting situations, you can assume a random permutation, maybe, but you need to be very careful doing that, I think. So I prefer to make minimal assumptions about the data sets other than the sort of obvious ones. Yeah.
Perhaps your property of randomization will only apply to algorithms which respect graph isomorphism. So if you're trying to compute a result that doesn't respect graph isomorphism, your randomization argument won't work.
Yes. Yes.
So there is a property of the algorithm which gives it this.
Or there's a property of the problem that you're trying to solve. The problem that you're trying to solve needs to be invariant under isomorphism. That's true. Yes.
Can I be greedy and say, for the disjoint union problem, does it change completely if you actually want to be able to remove nodes? So it gets a bit more complicated if you want to add things to the set of nodes as you run. But if you want to remove things from the set of nodes, does it just become a completely different problem?
Removing nodes, you're also removing edges. You're removing all the edges incident to the node. So that's the same as the dynamic connectivity problem where you can add and delete edges, essentially. And that's the one for which there are beautiful polylog time algorithms. I think the best bound, there's a deterministic algorithm which is maybe log squared per find, and a randomized algorithm which is maybe log n per find by Mikkel-Thorup. It's a beautiful problem, and it's not well understood, but there are strong results there. And generally speaking, undirected graph problems are much easier than directed graph problems, and this becomes more so when you get into dynamic graph problems. And incremental problems are easier than deletion problems. For example, if you look at a simpler problem for directed graphs, keeping track of strong components, strongly connected components. There are the static problem you can solve in linear time. The incremental problem, the best algorithms depend upon the graph density, and it's roughly square root of the number of edges time per edge to do finds. And there are results on the dynamic problem where you can both add and delete edges, but they're not very satisfying, I would say. Again, I can send you references if you're interested in specifics. Any?
Thanks.